Picture a model that passes every test you throw at it. It classifies, it answers, it scores green on the eval dashboard, and then one day, someone shows it an image with a small yellow sticker in the corner, and the fraud detector that's worked flawlessly for 6 months suddenly waves the transaction right through. Nothing was hacked at runtime, no firewall was bypassed. The failure was trained in months earlier. A handful of poisoned examples that taught the model a secret rule. When you see this trigger, ignore everything you know. That's a backdoor, and the unsettling part is the model looks perfectly healthy until the attacker decides it shouldn't be. Today we're going to take apart how data and models get poisoned, at training, at tuning, and even in the retrieval index. And, just as important, how you catch it before it ships. Let me tell you where we're headed. By the end of this episode, you'll be able to do 3 things. First, name the 3 poisoning surfaces, the training data, the model's own weights, and the tuning and retrieval inputs you adapt and pull from. Second, tell targeted poisoning apart from availability poisoning. And third, list the defenses and know exactly where each one belongs in the pipeline. Here's where this sits in the series. Back in episode 4, we built the secure lifecycle and made the case that data security is model security. Well, this is the episode where attackers come for that data. Poisoning is the canonical train time attack. The adversary corrupts what the model learns before it ever serves a single request. And remember the thesis of this whole series. SecAI Plus is a security architecture for AI exam plus framework fluency. Poisoning isn't a product you buy a box to stop. It's a risk you design controls around at specific gates mapped to OWASP LLM04 and to MITRE Atlas technique AML.T0020. Learn the gate, not the gadget. One scope guardrail before we dig in. Today is about corruption that happens during learning and retrieval. How a poisoned model or dataset gets delivered to you through a model hub or a package, that's the supply chain, and that's episode 9. Attacks that manipulate a finished model at inference time, adversarial examples, evasion, those were episode 5. Here, the damage is baked in. Let's start with training data poisoning, because the mechanism is simple to state. A model learns the statistical shape of its training set, so if you can inject, alter, or mislabel even a slice of that set, you can bend what the model learns. You never have to touch the algorithm. You change the data and the algorithm faithfully learns your lie. Here's the visual that makes it click. A classifier's decision boundary is just a line drawn to separate good from bad. Drop in poison samples, mislabeled points or carefully crafted ones, and you drag that boundary across. Things that used to land on the malware side now sit on the benign side. Same model, moved line. Now here's the contrast the exam loves, because there are 2 very different intents behind poisoning. The first is targeted poisoning, and it's surgical. The attacker wants the model to fail on one specific thing, one user, one input pattern, one trigger, while staying perfectly accurate on everything else. It's quiet by design. Overall metrics barely move, which is exactly why it survives a casual evaluation. The second is availability poisoning, and it's blunt. The goal there is to degrade the model for everyone, wreck overall accuracy, make it unreliable, deny the service its value. It's noisier, but it's devastating, and sometimes the whole point is simply to make the system untrustworthy. To make this concrete, think about your real-world surface, anything trained on data you didn't fully control. Scraped web text, public datasets, user-submitted content, feedback loops where the model retrains on its own outputs. Every one of those is a place an adversary can slip examples in. So what is data poisoning? It's the deliberate corruption of the data a model learns from, by injecting, altering, or mislabeling examples, so that the trained model behaves the way the attacker wants. Because the model is shaped by its data, poisoning the data poisons the model, and it does so before the system ever serves a single request. Now let's take that targeted attack to its logical end, because that's where backdoors and trojans live. A backdoor teaches the model a hidden if statement. Normally, behave correctly, but when you see this specific trigger, switch to the attacker's chosen output. And the trigger is arbitrary and secret. A pixel pattern, a rare word or phrase, a special token, even an inaudible audio cue. Here's why it's so dangerous. On every normal input, the model is genuinely good, so it sails through testing and it earns your trust. The malicious behavior only ever appears when the attacker presents the trigger. They hold the key, and you simply cannot test for a trigger you don't know exists. Now, this isn't only a train from scratch problem. There are two modern surfaces I want you to watch. The first is fine-tuning poisoning. Most teams don't train base models, they adapt them with a smaller fine-tuning or instruction dataset. And that dataset is smaller, often less scrutinized, and frequently third-party or user-contributed. That makes it a cheaper, easier place to plant a backdoor than the original training run ever was. The second is RAG index poisoning. A retrieval-augmented system doesn't bake everything into its weights. It pulls from a knowledge base at query time. So poison that index, slip a malicious document into the corpus the model retrieves from, and you've poisoned the system's answers without ever touching the model. The weights are pristine, the knowledge is corrupted. And one scope reminder so this doesn't blur together. A poisoned document that injects instructions the model then obeys at query time, that's indirect prompt injection, and that was episode 7. RAG index poisoning here is about corrupting the knowledge the model treats as ground truth. Related vectors, different mechanism. So what is a model backdoor? A model backdoor, also called a trojan, is a hidden behavior planted in a model during training or tuning so that the model performs normally almost all the time, but flips to an attacker-chosen output whenever it sees a specific secret trigger. The model passes its tests precisely because the malicious behavior stays dormant until the trigger appears. One thing worth flagging for the exam: hold the targeted versus availability distinction firmly. Targeted poisoning, and its sharpest form, the backdoor, makes the model fail on one specific trigger, while overall accuracy looks completely fine. Availability poisoning degrades the model for everyone, and the giveaway in any scenario is the attacker's goal. Surgical and stealthy points you to targeted or backdoor. Broad degradation points you to availability. Now let's pair every attack with its defense, because that's the rule of this series. There's no single switch for poisoning, so you have to think defense in depth, across the same life cycle we built in episode 4. Start with trusted sources. Control where your training, tuning, and RAG data come from. The cheapest poison to stop is the data you never let in, so vet and authorize your sources before they ever reach the pipeline. Next, data validation and provenance. Validate and sanitize incoming data, and keep a verifiable record of where every dataset and document came from and what happened to it along the way. If you can't trace it, don't trust it. Provenance is what lets you answer the question, could this have been tampered with? Then, anomaly and outlier detection. Poison samples often look statistically odd. Mislabeled points, clusters that don't fit, examples that disagree with everything around them. Outlier and influence analysis on the dataset can surface them before training ever starts, and you watch the retrieval index exactly the same way. And finally, the one the exam keeps returning to, evaluation gates before promotion. No model gets promoted to production until it passes evaluation. Accuracy, robustness, bias, and, wherever you can manage it, backdoor and trigger testing. The gate that can say no is your last line of defense against a poisoned model ever reaching users. That's NIST AIRMF measure, and it's the same eval gate idea from episode 4. Map all of this cleanly. The whole picture is OWASP LLM04, data and model poisoning, and the training data attack itself is MITRE Atlas AML.T0020, poison training data. Name the framework, then name the control, and tie it back to the thesis. You don't patch a poisoned model. You architect the pipeline so poison is hard to insert, easy to detect, and can't pass the gate. That's the architecture lens applied to the data supply that feeds the model, which is exactly the on-ramp to the supply chain next episode. So let me leave you with 3 takeaways. 1. Poisoning corrupts what the model learns, across 3 surfaces: the training data, the model itself as a backdoor, and the tuning sets and RAG index you adapt and retrieve with. 2. Know the intent. Targeted poisoning, including the backdoor with its hidden trigger, fails on one specific thing while looking perfectly healthy. Availability poisoning degrades the model for everyone. 3. Defend in depth. Trusted sources, data validation and provenance, anomaly detection, and an evaluation gate that can refuse to promote a model. That's OWASP LLM04 and Atlas AML.T0020. Next up is Episode 9, AI/ML Supply Chain Security, where we follow the poison upstream and look at how a tampered model or dataset gets delivered to you in the first place. If this helped, subscribe and drop a question in the comments. That's the Architecture Lens. I'll see you in the next one.